so I'm going to let her introduce herself because she can say all the fun things about herself, other than that she likes birds.
Other than that?
Yeah. And also, we are going to be live streaming this on Facebook so that our Facebook friends can see what Rachel does here too. So without further ado, here is Miss Rachel Roth.
Hey everybody, I guess I have to tell you things about me besides the fact that I like birds. So my name is Rachel. I work here at the Great Plains Nature Center, and birds are my absolute favorite topic. I studied wildlife biology at K-State University and worked as a field biologist doing some field research, mostly on birds, go figure, before coming to the Great Plains Nature Center, where I discovered that my true love is sharing all of the cool things that I like with other people. So fortunately, I have a job now where people pay me to tell you about the cool things I like. So let's get going, I guess. Today, you all know why you're here. We are going to be learning that the chickadees you saw coming in on the sidewalk before you entered this building are in fact dinosaurs, which is, no exaggeration, one of my absolute favorite things to talk about, as all of my friends in this room can attest to, because I think it makes birds just even more exciting than they were before knowing that they were literally dinosaurs. So, our goal today is to understand that this tiny little bird is in fact a fearsome ancient beast. So congratulations, birds. You are a fearsome ancient beast. All right, so before we get into the dinosaur part, let's learn a little bit of backstory about how we got here. When the first dinosaur footprints were discovered, this was before the word dinosaur was even invented. We thought that they were just bird footprints. You'll probably want to turn off the lights just in the back of the auditorium because the slider's broken. Yeah. They're trying to figure out the lights back there. So when we saw these footprints, scientists looked at that and they said, oh, obviously those are bird footprints. And there was some reason to think this because, of course, back in the day we knew of moas. This is a recreation of what a moa hunt might have looked like in New Zealand. And we knew that these birds existed, and so footprints like these seemed like, oh, well, obviously it could be a bird. Of course, now we know that the proper posture of the moa was this, but this bird was so recent that even though we have no, like, necessarily modern records or photographs or anything of a real moa, we do have their eggs and feathers from the upland moa and other moas. So, yeah, these are actually fossilized footprints of the moa in New Zealand. But we did have dinosaur bones, and of course, as you are probably aware, our depiction of them was less than exciting. We kind of saw them as slow, plodding reptiles. That was the 1957 T-Rex, so it took us a long time to realize this was not actually the case. This is one of my favorites. I know, that's what we used to think of dinosaurs as being like. What really changed things for us was Deinonychus, or Deinonychus, depending on how you pronounce it. In 1964, Deinonychus was discovered, and this sparked what we call the dinosaur renaissance, which truly transformed our vision of dinosaurs. We noticed that, hey, those feet with those sickle-shaped claws, the posture, it reminds us a lot of birds, and it kind of resembles more of a fast, agile, active predator and not the slow, plodding Tyrannosaurus we had envisioned before. So with that discovery, we took another look at dinosaurs and realized that their sleek bodies, their horizontal posture, because of course their tails didn't drag, we have no footprints of their tails dragging, everything indicated that they were less like this and more like this in actuality. And Jurassic Park, of course, was one of the most significant transformative events in bringing the dinosaur renaissance from a conceptual thing that only scientists really understood to the public view. And that's when we got really excited about the study of dinosaurs. There's another version. I love these guys. So I'm going to show you, remember this is Deinonychus. Previously, of course, they were described as being very scaly. This dinosaur is often referenced as being what the Jurassic Park velociraptors actually were, because true velociraptors are much smaller. Here's a modern depiction of what we know Deinonychus probably looks like now. Yeah, vastly different. All right, so I'm going to show you a video clip to kind of introduce this transformative view of dinosaurs that got started back in the 60s. And this video always gives me the chills, so I'm very excited. Let's get going.
For about the last 30 years, people have started to look at the way in which the bones really document the evolutionary transition between traditional dinosaurs and living birds. But today we're able to really study living birds in a whole different way, as well as fossils. We're able to use CT data, CAT scan data to be able to take new looks at the bones, build computer models to be able to look at how the animals may have flown in the past. We're even able to use other kinds of data to look at the brains of these ancient dinosaurs and see how they compare with birds today.
Birds, although they might seem ordinary because we see them all the time, they're actually really extraordinary creatures. They have a lot of specialized qualities. These traits come from dinosaur ancestors.
There's so many striking bird-like qualities in dinosaurs. In terms of their skeletal structure, they had hollow bones and many features that are now used by birds for flying, but in dinosaurs were used for all sorts of different things.
Most dinosaurs have feathers. There's very close relatives of the Tyrannosaurus rex that have feathers. There's even much more primitive dinosaurs that have feathers.
In living birds, we know that feathers are used for many different functions. They're used for locomotion, but they're also used for camouflage and display and for thermoregulation. And probably all of these functions were important during the evolution of feathers as well.
Dinosaur eggs and nests are a really unique source of data, including specific nesting styles and egg shapes, the arrangement of eggs in a clutch, and then in other cases where we have an adult dinosaur preserved on top of the eggs, we can infer things about whether this dinosaur was brooding or not.
By the time the birds evolved the ability to fly, they already had a flight-ready brain, because we've been able to show that even much more primitive things that didn't have the ability to fly, things like Velociraptor, Troodontids, Oviraptorosaurs, all have a brain which is identical to the earliest birds.
The dinosaurs didn't go extinct 65 million years ago. We still have them around today. You can see them in your backyard, you can see them everywhere.
Am I the only one that teared up a little? Okay, so I'm so excited. Let's dive into this and learn something about our 2020 understanding dinosaurs. First, we need to figure out what the heck a bird is. So I'm going to give you a checklist of what a bird is. It includes things like they are warm-blooded vertebrates. So they have a backbone, they're warm-blooded. They have a beak, they have wings, they have bipedal locomotion, so they walk on two legs, which is actually fairly unique. They have hard-shelled eggs, feathers, pneumatic bones, which we'll talk about later, and circular respiration with air sacs, which is a mouthful. Don't worry, I'll get into that. But a lot of other animals have some of these traits. Humans are bipedal, but we're not birds. Mammals are warm-blooded, but they're not birds. So the things that are exclusively bird traits are these things right here. Feathers. Only birds that are alive today in terms of animals that are still on the planet in living form, they're the only animals that have feathers, the only animals that have pneumatic or air-filled bones, and the only animals that have this unique respiration system. All right, so that's our uniquely bird checklist. I also want to define a couple of traits for you guys because we're going to use these words quite a bit during the presentation. So the first word is theropod, which is a word that we use to describe all dinosaurs that walked on two legs that were carnivorous. So that includes things like T-Rex and Velociraptor. If it looks like that, it's probably a theropod. The other word I want you guys to know is avian, which just means bird-like. That's a pretty standard word. All right, there you go. And I do also want to let you know that there are 10,000 living species of theropods on the planet today. They are birds. The largest one is the ostrich. So, pretty cool. Also, theropods are either avian or non-avian. So if you are a bipedal carnivorous dinosaur, you can be basically like a bird, like Anornis up here, an avian dinosaur, or you can be non-avian, like this Bipalosaurus. And basically that's scientists' way of squinting at the fossils and saying, are you more like a bird or are you more like a dinosaur? And it's actually a pretty difficult distinction to make, as we'll get into, because there's another grouping, which is actually taxonomic, called paravian, and para means like near. So these guys are near birds, and Paraves is actually an entire branch of the phylogenetic tree that includes all dinosaurs / birds that are basically birds. And it includes things like Velociraptor. So the distinction gets kind of weird. But my goal today is to go through at least the uniquely bird traits and to examine how those fit into dinosaurs, starting with bones and respiration, because this is the most fascinating part to me. So, as you know, birds have hollow bones. That's a bone that's a cross section there. I've got some up here on the table if you want to poke around with them and check them out. Birds are not the only living animals that have hollow bones. We are an example of one that also has hollow bones. They're called our sinuses. And basically it means that part of our respiratory system extends into passages in our face. That's called pneumatization. So pneumatic basically means it's full of air. And it really is full of air because it's connected to our respiratory system. And plenty of animals that are alive today have hollow bones in their face, but birds are the only animals that have hollow bones outside of the face, including their arm and leg bones. Now, looking at the fossil record, this is also true of dinosaurs. In fact, having hollow bones is a theropod trait. So every single theropod has hollow bones. It took us a while to figure this out because we don't like breaking nice fossils. But you know, with the use of CT scans and things like that expanding, we've begun to realize this is just a basic trait of theropods. Here's another example of one that had quite a few hollow bones, and here's a drawer full of just hollow theropod bones. So here's what's crazy though, it's not just theropods that have these hollow bones. Pneumasticity, or air-filled bones, is present in big theropods like Tyrannosaurus rex, of course, but also things like sauropods. Long-necked dinosaurs also have hollow bones. Amazing. It's present in pterosaurs as well, which is not a dinosaur, just so you know. Yeah, I saw somebody mimicking my brain explosion. I'm glad that I'm not the only one. Even if I was the only one crying over the video, it's fine. So this is not just a theropod trait, it's a dinosaur trait, that many dinosaurs had these hollow bones. So why do dinosaurs and birds have hollow bones? We're probably thinking, to make them lighter so they can fly, because that's a pretty popular story, and it might aid at least some birds in being lightweight for flight. However, there's a more important reason, and it has to do with bird lungs. So bird lungs are very, very different from ours. Our lungs, air comes in, and then air comes out. I want everybody to take a really deep breath for me. Now breathe out. Now breathe out again, and again. Yeah, that's called dead air. We can never completely remove all the air from our lungs. So that's a lot of wasted space of not fresh air, stale air that gets stuck in our lungs. Birds don't have that problem because they have a system of air sacs, which is very hard to describe, so I will show you a video that will kind of walk us through how birds breathe. But basically they have a lung at the top of their back, which does not expand like a balloon. It's rigid. And these air sacs are kind of like bellows. They have no oxygen exchange or anything. They're just like empty balloons. And they push the air in and out of the bird's body. Now, what's crazy is that this air sac system invades a bird's bones. So kind of like how our respiratory system invades our sinuses, the same thing happens with birds, but they have sinuses throughout their entire body that are connected to their respiratory system. Now, what makes this crazy is that birds actually have circular breathing, which is not the same as circular breathing you can use to play a didgeridoo. It's completely unique. And it's also different from lizards and most reptiles except crocodiles, but that's a side note that I will not get into today. So instead of trying to describe how the heck birds' lungs work, I'm going to show you an animation and we'll get through it together.
The path of a breath through the system can be summarized in 4 steps. During the first inhalation, the breath travels down the trachea, into the left or right bronchus, through the lung, and into the posterior thoracic and abdominal air sacs.
The butt air sacs.
As the bird exhales, the abdomen contracts, forcing the air out of the abdominal sacs and into the lungs. Within the lungs, the air passes through parabronchi and eventually through air capillaries. It is only here where the exchange of carbon dioxide for oxygen occurs. As the bird inhales again, the air within the lungs is driven out. The now stale air passes into the interclavicular, cervical, and anterior thoracic air sacs.
The chest air sacs.
During the second exhalation, the anterior sacs contract. The air is then driven out into the trachea, where it passes up and out of the nostrils. This specialization of the avian respiratory system is one of the greatest factors in flight. Without this unique anatomy, the act of flight would likely be impossible.
Pretty cool. So in like normal people language, basically it takes a bird 2 inhalations and exhalations to get the air in its body and out of its body. The other important thing we need to know because of this is that air is constantly moving through a bird's lungs. Fresh air. They don't have that dead air problem that we have because it's not coming in and out the same way. It's going through the lung in one direction, which is why they can have such high metabolisms and can definitely help us explain how the heck hummingbirds manage to do what they do. So pretty amazing. Now here's where it gets crazy because dinosaurs have hollow bones for the same reason. We first realized this fully because of the discovery of Arostion in 2007. That's its skull. And we discovered that the holes leading into the bones, because remember, these are connected to the respiratory system. So if you take like one of these regular goose bones up here, if you look at it, you'll find holes in it. That's where the lung system goes into the bones. So that's not something that we drilled into it. So the same thing is present in dinosaurs, which in the same locations as modern birds shows us that they had the same air sac system going into their bones. So comparing these two, we realized Arostion actually had those chest air sacs and those butt air sacs and a rigid lung that was situated right up here. So dinosaurs have bird lungs, or maybe we should say that birds have dinosaur lungs. This is amazing. Here's a comparison to a sauropod and a swan vertebrae, because sauropods also have hollow bones. Remember, those are the long-necked dinosaurs, and it turns out they also have bird lungs. So they have air sac systems. We can find the hollows for it, and their air sacs actually go all the way up their neck and down halfway through their tail. And we know that these are connected to their lungs because if bones are not connected to a respiratory system, the hollow fills up with bone. So these are part of their lungs. Crazy. And maybe helps us explain how the heck sauropods could keep those necks so elongated. So dinosaurs have bird lungs and they have bird bones. Awesome. Let's talk about feathers. So feathers is probably what we are most familiar with. This is a fun name. But we maybe don't realize the extent of dinosaurs that had feathers just because so many of the discoveries have been fairly recent, and it's not always super obvious to our untrained eyes looking at some of these fossils what the structures mean. But we have like so many like birds, dinosaurs that have feathers. It's cool. So we're familiar with Archaeopteryx. This is the famous 1861 specimen that had those beautiful flight feathers. What some people don't realize is that we actually have 11 of these specimens, including a straight up feather that's just from the Archaeopteryx. Here's another specimen of Archaeopteryx that we had. I think this one was found in Germany. And here's another Archaeopteryx. So what's kind of interesting is that these guys were discovered actually, do I have it on here? I do. The first T-Rex was discovered in 1905. So we actually had Archaeopteryx before we had T-Rex. We just thought it was a bird and didn't realize how significant the find was. They were discovered and described about 2 years after the origin of species by Charles Darwin, so there had to be a revision made to that original text. And since the discovery of Archaeopteryx, we have unearthed thousands of feathered dinosaurs. And they're not always these fancy flight feathers that are really recognizably bird-like. This is an actual scientific word I'm about to tell you, dinofuzz. This is a type of what we consider a more primitive dinosaur feather. We see, this is the Selenocosaurus, I think is what it's called, that was in the video, that had these long, hollow filaments on its tail. So a lot of dinosaurs just had straight up fuzz. It's such a primitive feather that it doesn't even look like a feather. It's just like long, hollow hair. So it's definitely a feather-like structure, but it looks more like hair. Scientists usually describe these as being kind of like duckling feathers and stuff like that. So if you can imagine, that kind of puts it into a context that our brains can figure out. So some dinosaurs had dinofuzz, some had straight up flight feathers and wings. And we've pretty well figured out the origin of feathers. Actually, we know that there is a structure that grows out of bird feathers that is actually present in reptile scales as well. So that helps us to figure out how in different lineages of dinosaurs feathers could appear at different times. Here's just another little diagram here showing different evolutionary pathways for the development of feathers, including just, you know, dinofuzz. But what's really crazy is that it's not just theropods that have feathers. If we look at the dinosaur tree here, we'll see some, I know it's kind of hard to tell, but I'll show you the important ones. These are showing you whether they had scales, filaments, the kind of fluffy feathers, or the wing feathers. And you'll notice up here, Ceratopsia has filaments. If you don't know what that is, you probably know what Triceratops is. That's that group of dinosaurs. There are members of the Triceratops family that had filaments, dinofuzz. Also, interestingly, pterosaurs, again, which are not a dinosaur, they're much further diverged from dinosaurs, they also had dinofuzz. So not only did they have those bat-like membranous wings, but they were covered in little filaments of fuzz. So basically, this is a really, really basic dinosaur trait that's not just for theropods. And if we look at the evolutionary tree here of these guys, we've got some really primitive bird-like archosaurs. Crocodiles are the nearest living relative of birds, which, fun fact, also have circular breathing, just with no air sacs. But if you see here, pterosaurs have feathers. Feathers emerged many times in this lineage. So here's a great quote that I really like by National Geographic. It says, "Perhaps the question to ask is not how birds got their feathers, but how alligators lost theirs." That's how basic feathers go. So I'm going to show you a few of our feathered dinosaurs that we have, because I think they're pretty neat. Anchiornis might be one of my favorite dinosaurs, but here's some beautiful specimens that were preserved from this little animal. I have an illustrated version of Anchiornis later on. This is Microraptor, which had 4 wings, so they had wings on their legs as well as on their arms. Sometimes putting things under UV light can help us reveal other structures as well. Cool little bird. This guy is Cynornithosaurus. Cynornithosaurus. Wow, dinosaur names are getting complicated. Although, kids know these names like nothing else. It's kind of amazing. So this little guy is really important. We'll talk about him more later, but he had dinofuzz. Here is Gymphangopteryx. A lot of these animals were discovered in China that have the really well-preserved feathers. And Caudipteryx, which you can see has these beautiful tail feathers out here preserved. Even Velociraptor, we know, had feathers. And the problem with our typical dinosaur fossils that we probably envision is that a lot of the ones outside of China were preserved just as bones. So they're kind of naked. But because of these amazing specimens we've been finding in the last couple of decades from China and other places that have really well-preserved fossils, we see not just feathers, but skin preserved. So with Velociraptor, what's definitely cool about them is we know that they had feathers because this is a turkey bone right here, and these are the velociraptor bones. They actually had what we call quill knobs, which are attachment points for flight feathers. Now, why this is cool is because that's where the muscles that control their flight feathers attach to the bones. So basically this means Velociraptor probably could control the feathers on his wings, similar to how modern birds can control their flight feathers. Ooh. So, here's another one. This guy is Zhen Longlong, who is Velociraptor's cousin, and another good piece of evidence why Velociraptors definitely had feathers, because everybody else around them absolutely did. Here's a nice illustration of that animal. Ooh, they're so beautiful. I also really like Oviraptorosaurs. These guys might just straight up be birds. There's a whole bunch of them. This one you might recognize because they were thought to be egg thieves for quite a long time because they were discovered on top of a nest, which later turned out to just be its own nest because these guys just incubate their nests and they nest in colonies. Here's a modern depiction of one of those little guys with feathers. They had feathers all over their body. Gymphangopteryx earlier with those beautiful tail feathers was one of these guys. But what's extra cool is that they have some fused bones and a beak, a toothless beak, and other traits that are very bird-like. And so they're so bird-like that even though we know that they're a more primitive lineage of dinosaurs, in 2002 in particular, scientists were really arguing hard to make this classified as like just a straight-up bird. It was proposed to be in line with Archaeopteryx in terms of its bird traits. Really cool little animal. Oh, and there's a cute little tiny one on its little eggs. Now, it doesn't stop there. So not only do we have fossils of the feathers, but it took us a little while to realize that these structures we were observing under microscopes were not bacteria. These structures found in the feathers are pigments. So we actually know the color of many dinosaur feathers. The feather specimen that clued us into this was this one right here, because you could see the deposits of melanin on these dark stripes, and then under the microscope, that's where those melanin pigments were present. Amazing. So the first dinosaur, to have its colors described by science, was Sinosauropteryx. And we looked at the dino fuzz and determined that it had a striped red and white tail and reddish brown feathers on its body, and that the underside of the dinosaur was lighter in color. Okay, now Anchiornis, which I did not show you a good picture of the feathers earlier. This guy has had its colors described by science too. You can even see the melanin deposits right here. So looking microscopically at this, we determined that this is probably the real life color of Anchiornis. Isn't it so cool? We also know Archaeopteryx's colors. Prepare yourself. So here's our Archaeopteryx. In 2011, we found its colors, and it was also very dark. Ooh, so that's super, super neat. And notably, a lot of these animals, kind of like with birds, some of the colors that they have are actually structural on the outside of the feathers, so it kind of reflects light. Like if you view a bird in shadows that's blue or purple, when it goes into the sunlight, it might suddenly look very bright, like a blue bird or a blue jay. And there's iridescence in birds as well that's structural. So we've also identified structural colors on the feathers, and we did, in fact, have rainbow iridescent dinosaurs. Just throwing that out there. So I know what y'all are thinking. Did Tyrannosaurus Rex have feathers? Everybody wants to know, because for some reason people think it can't be ferocious if it's covered in feathers. Like a giant T-Rex bird wouldn't terrify you. So as far as we know, we did discover some skin imprints of the Tyrannosaurus Rex in 2017. Here is an imprint of its neck, and here is an imprint of its tail. And as far as we could tell, all of the imprints from Tyrannosaurus specifically, did not have visible feathers. But we did not find some of the parts of the animal that typically have feathers in some of the other dinosaurs. And it's been hypothesized that they probably had some sparse filaments, kind of the way elephants have very, very sparse hairs. If you had fossilized imprints of elephant skin, those fine structures probably wouldn't have been preserved as easily. We also know that Tyrannosaurus had cousins like Eutyrannus, which absolutely had feathers. So its family members all had feathers. Here's another illustration of Eutyrannus. So it's been hypothesized that T-Rex simply lost its feathers over time the way elephants lost their hair over time. Here's a juvenile specimen of Eutyrannus that was preserved. So this is the prevailing theory. When National Geographic did a TV program called T-Rex Autopsy, which, yes, is a thing that exists. They autopsied a fake T-Rex on National Geographic. They decided to cover it in goose quills that were sparse filamentous feathers, because that's what the evidence suggests so far for T-Rex. Okay, but it gets even cooler. We have amber feathers preserved, and not just feathers, we have entire dinosaurs and dinosaur bits preserved in amber. So here's some amber feathers, some close-ups of those amber feathers. This is a wing preserved in amber. Another one right there. And there's a close-up of one of the claws. I think, yeah, there it is. There's the claw on the wing for this dinosaur wing. And we even have an entire avian dinosaur hatchling preserved in amber. These were also in 2017. Here's a close-up of that little claw. Here's a close-up of its wing, and another kind of close-up of the body part that's visible. So we've studied this thing extensively through x-rays and things like that. Here's an illustration of the animal that's inside the amber. It is an Antiornithes, which was a toothed bird that was alive at the time of Microraptor. So that's really cool. It's got little tiny serrations in its teeth. The illustration didn't capture that, but the x-rays did. Also, we have a dinosaur tail in amber, which is really cool. This is a non-avian dinosaur. It was discovered the year before, in 2016. Here's a CT scan of the bones in its tail, and some close-ups of the feathers. And this is kind of cool too, because where the tail was cut off, you can see some ferrous, sort of like rusty colorations and stuff, and there's no DNA in it, but it is dinosaur blood. So that's very cool. Also, I had to include this thing that came out like January 17th of this year. This is pretty cool. This is a cute little guy. There's one of our scientists working on it. Its name is Oolong bohaiensis, which means dancing dragon. And what's really cool about this specimen is that it did have, here's an illustration, flight feathers. Oops, what did I do? There it goes. It had flight feathers both on its wings and its legs, and a very long tail, which is really cool. A lot of dinosaurs had like long feathery tails and feathers in its body. But what made this so crazy was that they studied the bones, the histology of the bones, like the age of the bones, which is pretty destructive, so we don't typically do this. But that study revealed that this is actually a juvenile animal, and juvenile in the sense that it's still growing. So this bird is not finished growing yet. This dinosaur, sorry, same thing. Which is very interesting because, as you guys might know, birds don't develop their full feathering until they're adults and they're finished growing. If you see a bird and it's got flight feathers, it's not getting any bigger, it's stopped growing. It might still be technically a juvenile because of colorations and sexual maturity and things like that, but it's finished growing. So this means that dinosaur development from young into adulthood could be really different from what birds were. And it might mean that we're going to be taking a closer look at some things we've studied already to decide whether some of the dinosaurs you described were in fact actually juveniles and not fully grown. So that's really cool too. So we know a lot about their feathers. So let's go back to our dinosaur or bird checklist, same thing, and go through it. So we know they have feathers, we know they have pneumatic bones, circular respiration, but what about all these other things that we talked about? I'm going to quickly go through a few of them just because they're easy to talk about real quick. But beaks, kind of went in and out of dinosaur lines all the time. So here's a straight up dinosaur that had a bird-like beak. Here's a straight up bird that had teeth and a jaw structure similar to dinosaurs. We have this little guy who's Ichthyornis. He's really cute. He's a Kansas find, and we discovered a fossil that was really well preserved here in Kansas recently of its jaw, which kind of showed some really cool development between the jaws of dinosaurs like Archaeopteryx and modern birds. So yeah, beaks came in and out of existence multiple times in the dinosaur realm, and birds still have the genes for teeth. There have been some controversial studies looking at that in embryos. Okay, are dinosaurs warm-blooded? Are they cold-blooded killers? This is actually highly debated because we don't really know where to draw the line on these things, but there's some very good evidence, not just in the bones of the dinosaurs that they were warm-blooded, but in some of the context clues. For example, Eutyrannus that when we looked at earlier, that lived in the Arctic and was covered in feathers. So good evidence that it was warm-blooded. Also, we have birds that were in positions of incubation over their eggs. So that's another good clue that there was some warmth produced by the body. Also, the presence of dino fuzz in juveniles that is somewhat lost as adults, suggesting maybe the younger one is needed to retain some warmth. So there's a lot of good clues. Evidence is kind of complicated. We're still sorting this out, but at least some dinosaurs were definitely warm-blooded. What about bipedalism? Okay, this sounds really easy because obviously they walked on two legs. But I did want to bring this up because this is something that's very uniquely bird-like. I do have a video to play you called Crouching Turkey, Hidden Dragon. It's just like a 1-minute clip kind of examining the morphology of bird legs.
I'm interested in things walking on two legs, which, I mean, in the modern world is basically limited to us and birds. When humans walk around, we tend to walk around with fairly straight legs. Our legs act somewhat like a column. So they support our weight using mainly the bones. It's a fairly straight line from our center of mass, the average position of our body weight, straight down the leg. Whereas when birds stand, they have very bent legs, these very zigzag legs, which mechanically is slightly counterintuitive because it takes a lot more muscular effort to stand like that.
All right, time to see the birds. Yeah, check out the posture of the leg is really interesting. The knees there, and then we go down to the ankle, and of course the toes. So it's a very crouched posture with the, especially the hip and the knee very bent. The thigh almost horizontal like this. So I got a posture like that.
The question.
Yeah, so that's a very unique thing, and a lot of people don't realize that birds' knees are up by their body. I don't know if you guys saw, there was a meme going around where people took an owl and they lifted up its skirts and it had these very long legs revealed because they typically crouch down and cover their legs with feathers. But birds have incredibly long legs. Their knees are almost horizontal with their thigh right there, and that's a very unique posture that only dinosaurs have, in addition to birds. Also, I mean, this is amazing. This is a foot of a dinosaur. Let me look at my notes. Oh, this is Anchiornis, the one that had the red crest and the black and white feathers that had the 4 wings we looked at earlier. And this is one of those dinosaurs that's an avian dinosaur. So it was a toothed dinosaur. It had hands and things like that. This is its foot. And of course you can see the bones here. Those are the toes. But you can actually see the skin right here as well, the outline of the skin for those toe pads. And this was a study in 2017. People are developing new technologies to look at bones that have been sitting in cabinets for ages in a brand new light, literally. They actually took the Blu-ray disc player light and used that technology to develop a really high-powered UV light to look at dinosaur bones and reveal under that different light structures that were invisible to the naked eye. So here is this dinosaur foot under UV light. I got shivers. Yeah, you can see the little imprints of the toe pads. I mean, these are identical to bird toes and stuff, so that's just really cool. So back to our main question, are birds dinosaurs? The better question is, how on earth do we even draw a line? What is a dinosaur and what is a bird is really the question that paleontologists are asking now. And I guess to kind of describe that, there's a really cool podcast called PaleoCast, which interviews a lot of paleontologists who are doing the groundwork on a lot of these studies. This is Dr. Steve Brusati from the University of Edinburgh. This is an interview from 2014. He studies Archaeopteryx specifically, and we'll just listen to what he had to say about this.
So you wouldn't generally say that there's a cutoff between birds and dinosaurs. It's just sort of a continuum throughout. But how do you make the distinction between what is a non-avian theropod and what is an avian theropod?
Yep, you got it, totally. And that's the thing. When you only have a few fossils of something, you know, it's easy to kind of draw a line on phylogeny and say, well, these things are, you know, dinosaurs and these are birds. But all of these feathered dinosaurs from China over the past few decades, and also finds from other parts of the world, have really blurred those lines. And it's almost impossible, I would say it is impossible, to draw a line on the phylogeny now and say that these are dinosaurs below this line and these are birds above this line. What we call birds really is just a convention. This avialan note, Archaeopteryx and living birds and all descendants of their most recent common ancestor. That's really just a historical convention because Archaeopteryx was found so long ago. It's always been considered a bird, and it, you know, it does look like a bird. It does have wings and modern flight feathers and these kind of features, but that really is arbitrary. And I think if you were standing around in the Cretaceous and you were, you know, a Cretaceous bird watcher, Cretaceous dinosaur watcher, let's say, you had your pair of binoculars and you were, you know, looking at some ecosystem and you saw a velociraptor type animal and you saw, say, a Confucius ornis type animal, Confucius ornis being an early bird, I don't think you would make any distinction between them at all. I think you'd consider them the same type of thing.
Yeah, the same way we look at ostriches and chickadees and say, yeah, it's about the same type of thing. Those are both birds. They both have distinct traits. And looking at our modern birds, in some animals, we would consider them primitive because they retain a lot of those traits. It's still heavily visible. We saw a clip of these guys in that first video we watched. This is Hoatzin, which is a real bird. I know they looked like puppets in that video because they look like they shouldn't be real, but this is a real bird. And I want you to look at it again through your dino vision goggles. As youngsters, they actually have claws on their wings that they use to climb on tree branches, and that's a really cool bird. I have a quote from Mark Norrell, who is, he is the, I'm sorry, I'm looking for his qualifications. Oh, I have it on thing, okay. He's the American, he's from the American Museum of Natural History. He was interviewed in that first clip. He said, the more we learn about these animals, the more we find that there's basically no difference between birds and their closely related dinosaur ancestors like Velociraptor. Both have wishbones, brooded their nests, possess hollow bones, and were covered in feathers. If animals like Velociraptor were alive today, our first impression would be that they were just very unusual looking birds. And I think that brings me to my very last point, which is why does this really matter, and why does it get me, I guess, so excited, and why do I think it should get you so excited? And that's because we still have dinosaurs. They didn't go extinct, as Dr. Mark Norrell says. We just call them birds now. And if that doesn't make you excited about birds, I don't know what will. We still have dinosaurs prowling. They're crows, they're eagles. Yes, they are house sparrows too. But even those little house sparrows are actually dinosaurs. And the things that make them birds, that make them sparrows, are the same things that made dinosaurs like Velociraptor dinosaurs. So the next time you see one of these little guys and you're like, wow, I wish I could have prettier birds at my bird feeder or something, remember they're dinosaur ancestors, they're ferocious cousins, and thank your lucky stars that they don't have teeth anymore. And as a parting clip, I have a video for you. Thank you. Are there any questions? Thanks, Lori. She said you have the lights on so I can actually see you. Yes.
What about the Triceratops? Wasn't it a quadrupod?
Yes, it's a quadrupedal dinosaur, and that's why finding that those, I don't know that Triceratops itself has been found with feathers, but some of its very closely related group members that were also quadrupedal did have feathers. And that's why it's so amazing, because it shows us just how deep into our past feathers actually go. It's not just those theropods, it's a lot of dinosaurs before that. So the groundwork was laid even before we had those bird-like dinosaurs. Lindsay,
would you?
Sorry, go ahead.
Are there any dinosaurs that are not bird-like?
Yes. Well, probably. So we traditionally would view dinosaurs as, there was a tree at some point earlier that had like the crocodiles and the birds on each end, and then in between there was like that little branch. So after pterosaurs, we kind of consider most of those guys to be dinosaurs. So it's things like, I'm not going to list a bunch of dinosaur names because I don't think that would really help us here. Hang on. The things that you're probably imagining are dinosaurs. Those are all considered dinosaurs. And there were some very primitive dinosaurs. This is a good question. If you didn't hear the question was, are there any dinosaurs that are not birds? And I guess the modern answer would probably be that we have specific clades that we consider to be birds. So for example, the Paraves group, that includes things like velociraptors and those other guys, that is considered to be near to modern birds. And then within that branch, we have Aviales, which is a clade that includes Archaeopteryx and every bird-like bird dinosaur that came after it, and those are typically considered to be the true modern birds. So I guess it depends on where you want to draw the line of which traits belong to birds, because the ancestors of crocodiles and birds had somewhat similar traits in terms of how they laid eggs and their respiratory system too. So I guess all dinosaurs had at least some bird traits, but not all of our dinosaurs were bird-like. That was a very long-winded answer. Lindsay.
I was just going to ask you to repeat the questions when they come in.
Oh, okay. Thank you. I will repeat the questions when they come in. Yes.
They had a fellow on TED Talks where he was saying that with genetic manipulation of a chicken,
yes,
in embroid state, they go through a phase where they pass through dinosaur-like characteristics.
So
they may be able to turn on and off the gene.
I actually have a slide back here. I put all the cool things that didn't really fit in a different part over here. So he was bringing up that he's seen some talks that brought up those embryology studies where they looked at chickens and maybe modified some genes that were already present in the chickens, turning them on and off to look at different traits and how that changed their development. These are some of the images from those studies. They're dyed to make it easier to see, but there is the hand before it's fused. There is the longer tail before it shortens and fuses into the bird tail / pubic bone. And that's not even modified, so eventually it fuses and looks like this. But modified, oh goodness gracious, Rachel, let's keep going. Oh my goodness. Oh, here are some of the modified ones. So they've looked at the beak structure, and they modified some genes that were already present that completely changed the palate of the bird to help us look at some of those traits. And I didn't find a picture of this, but they did also turn on and off some genes that had some, what looked to be teeth developing in the beak, which again we know is something that a lot of very recent birds had, ones we found in Kansas even. But of course, we didn't let those birds grow up very far because it's, the ethics and the humaneness of that kind of study is pretty questionable. So they had just very early development of these chicks. But yeah, I've heard interviews from folks who worked on Jurassic Park talking about how they animated them based on chickens and how if you modify a chicken in the right ways, you could probably just literally recreate a dinosaur if the bird could survive to adulthood and not be in incredible pain or something. So yeah, interesting. Other questions? Yes?
Rachel, I have a comment. I came in late because it's helping put away tables.
Oh.
But if there's any art museum members here.
Yeah. Which art museum?
The
Ulrich?
Museum has, I saw a picture of a raven. And the Wichita Art Museum's having a program starting Saturday.
Okay.
This young lady could speak more to it.
I guess there's an art museum program starting recently that has to do with.
It's at the Wichita Art Museum.
Okay.
It's an exhibition and it goes through August 30th. But it's about it's Native Americans from the Northwest, and he has his whole exhibit, all of his artwork and everything is based on this story about the raven.
Okay.
And its cultural significance.
Cool. So if you're interested in learning about the cultural significance of the raven to native groups that lived in this area, the Wichita Art Museum has an exhibition, I don't know what they're called in the art world, that's open until August, so
But
definitely
they
check
also
that
have,
out.
like, Friday night is the opening night, which is a party for the artists, but then on Sunday afternoon, you'd have to look at the website, and you have to pay to get in, but you get to see the exhibit.
Cool.
His artist talk, and it takes like an hour and a half, and he talked about the significance of the bird and
Cool.
his art and everything.
Awesome. Any other questions?
Oh, I have a question.
Oh, go ahead.
Well, I was wondering, like, you know, we're always hearing about, all the dinosaurs went extinct, and so now, if we're seeing that we have, no, they didn't all go extinct.
Mm-hmm.
How did these guys? I mean, was there really a cataclysmic thing, or?
Oh yeah, for sure. Part of the evolutionary history of these guys was that, and this is like a whole other topic about like the environmental history of our planet and things like that. But basically, all of those large, very distinct dinosaur-like animals did go extinct, and it was a large cataclysmic event that's pretty well understood at this point. So if you want to go look into that more, there's some really interesting stuff. But that's possibly why only the very small ones that did develop into modern birds survived. I would also say that there are some pretty ancient lineages of birds that still exist on the planet. I was flipping through some slides that I hid at the end of my presentation there, and I will show you this one just because I learned it a couple months ago and it blew my mind. But these are terror birds, the largest of which was 10 feet tall, that were primitive, like running terrorizing bird, amazing animals. And we actually have one living descendant of the terror birds called the Siriema, which is in Brazil. And here's a video of one running. So we do have a literal terror bird that's alive today, which is pretty amazing. Like that predates moas and everything else. Like this is a very, very ancient group of animals that were hunting horses and other very prehistoric, like at the time of mammoths and things like that. Yeah, very, very cool birds. Yes?
One of the things that I'm always kind of amazed at is they never seem to address the issue of what appears to be a change in gravity.
A change in gravity?
Gravity. The pterosaurs, or I'm not pronouncing that right, some of those had a 40-foot wingspan.
Mm-hmm.
And there was every appearance that they flew.
Well, I haven't heard anything about some of those like really basic geological things like gravity shifting. However, there have been atmospheric changes, and with a lot of those animals, like with pterosaurs in particular, the way they were able to fly had to do with where they lived and hunted too. So kind of like the albatross, many of them would have taken off of cliffs and would have lived mostly over the seas, although there were some terrestrial pterosaurs. Those are the bat-like flying reptiles. And for those pterosaurs, we also know that they had hollow bones, air sacs, and other features. So they, had a lot of adaptations that allowed them to be able to fly. And so there were some different changes in climate and atmosphere that might have affected things too. But I don't know a whole lot about the environmental history of the planet. I just know about birds. Any other questions?
Does that bird fly?
Yes, it does fly, although not very well, and terror birds as a group are generally considered to be flightless. So it's not a strong flyer, it doesn't fly long distances, but kind of like a turkey, it can fly up into a tree. Yep.